Okay, I'm going to put socket programming in its own topic in the notes, which I'm going to call networks. So this is going to be page 1. We're not quite done with interprocess communication yet, but I'll come back to that after we cover networks and socket programming. So section 1 of this topic is the intro, and you've probably heard of socket programming. Sockets are an API, application programming interface, for network programming, and C and C++ share the same set of functions and data structures that you use. It's been around a long time. It's a little awkward to work with, but it's what we have. They're working on an update, and they have been for quite a few years, but it hasn't come out yet. So if you use a newer language like Python, you'll notice that socket programming is a fair bit simpler. Okay, so a socket address is equal to an IP address plus a port number. So the internet protocol stack has 5 layers. At the bottom is the physical layer, so that's going to be your medium, like wireless or cables or whatnot. And then on top of that is the link layer, which will be like Ethernet or what is it, 802.11 for wireless, and so on. Above that is the Internet Protocol layer, IP, and that's about addressing and routing, so getting packets of data from one host to another. They call machines on the internet hosts. And then above that is the transport layer, and that has to do with sequencing packets, making sure that they get to the other end in the right order, retransmitting lost packets and stuff like that. And so the two protocols there that are most common are TCP, the Transmission Control Protocol, and then there is the UDP, User Datagram Protocol. User Datagram Protocol really doesn't add much to the IP layer. You just fire packets and hope they get to the other side, and there's no resending or anything like that, whereas TCP gives you a reliable two-directional byte stream, and there's checks and resends and things get there in the right order and all that. So it depends on your application which is the appropriate one to use. And then the top layer is the application, whether you're writing a web browser or a program for this course or whatnot. IP equals Internet Protocol, and it has to do with addressing and routing. And if you find that stuff interesting, there's a course, EC 358, that I would recommend. It's quite popular. So the IP protocol has gone through a number of versions. So IP version 4 has been around since 1981. I think that was when it was first proposed or first released into the wild. Anyway, this is a 32-bit address, and for an example, you might see them written out like this: 151.101.2.133, and each of these groupings represents 1 byte. So that's 1 byte, and so it can have the value from 0 to 255. That's what an 8-bit unsigned number can give you. So you concatenate 4 of those together and you got a 32-bit address. This happens to be one of the addresses for uwaterloo.ca. I'll expand on that point shortly. So they realized that we're going to run out of addresses with 32 bits. You can have roughly 4 billion addresses, 2 to the 32. But not all the addresses get used because of the way the address space is divided up. And anyway, there's a lot of network devices out there now. So IP version 6 was released in 1995, and it uses 128-bit addresses. So it coexists with IPv4, so all operating systems have to have a protocol stack that can handle IPv4 or IPv6 packets. The intent was that IPv6 would have replaced IPv4 completely by now, but the rollout's been slower than expected. So in Canada, I think about half of networks are fully, up to version 6, but still half aren't, and we're kind of in a pretty good place compared to some other countries. So rollout has been slow. So both still exist and will for a while. And the way these addresses are written out is like this. So 2A04, that's hexadecimal, and I'll just write out the address here. 2A04 colon 4E42 colon 600 colon 645. I'll put slashes in the zeros of the 600 to indicate that they're zeros, not O's. And so this represents a 2-byte value, so the range is from 0 to FFFF. And here what we've done is we can omit the leading 0, and here the double colon says to skip the longest sequence of zeros. So in between that double colon there would be four 2-byte zeros. So it's just a way to shorten the representation without losing any precision. Okay. So next we want to talk about DNS. DNS equals the domain name system. Sometimes I call it domain name servers, but system. And the point of this is to map a host name like uWaterloo to an IP address. So the host names are there because they're easy for us humans to work with, but the IP protocol layer needs IP addresses, not host names. And when you do a DNS lookup, it returns a list of all the addresses for that host. And so some servers will have multiple IP addresses associated with the same host name. An example is uwaterloo.ca. If you do ns lookup uwaterloo.ca on a Unix machine, you'll get back 8 addresses, 4 IPv4 addresses and 4 IPv6 addresses. So I think that means that there's 4 machines, and each is running both stacks. So the lookup returns the list of all addresses. So some host names map to multiple servers, multiple machines. And so if you want to check out what I was just mentioning there, you can try this at the Unix command line. ns lookup, I think this network services lookup, uwaterloo.ca. Each I guess computer that requests a DNS translation gets back a full list of all the addresses, but the order of that list changes with each request to the DNS server. And you're expected to use the first one returned to you, and that way you can achieve load balancing with those servers. So yeah, if you ran that ns lookup uwaterloo.ca a couple of times, you'd see that they're in different orders, the returned list of IP addresses. And that's relevant to a function that I want to show you now. And it returns an int, and the function is used to do DNS lookups, and it's called getAddressInfo, and it takes a parameter called a node, and that's going to be the host name, like uwaterloo.ca, a service, and that's going to usually be a port number or a name for that port number, so 80 or HTTP, and then something called hints. It's a struct that says like what kind of connection you want, whether it would be TCP or UDP, and also whether you're interested in IPv4 or IPv6, that kind of stuff. So you give hints to get address info in that struct, and it returns a linked list of address structs that it calls res, short for result. So the node is a const char pointer, it's a string. So is the service, const char pointer. So node, for example, could be uwaterloo.ca, or another one, a local host. That's the loopback connector, so that's going to actually give you your own machine, and there's a special IP address for that. In version 4 it's 127.0.0.1, and in IPv6 it's just :1. Anyway, sometimes you want to like test things and just connect to the same server on the machine you're running on, so that's useful there. The service can be a port number like 80, and I'll expand on port numbers fairly soon, or the name of the service. So I think web might also work, or www, HTTP, or it could be IMAP, for example, for a mail server, etc. So hints is your preferences, and I'm going to have to squeeze this in here. It's of type const struct address info pointer, and the result has the same type, so it's const struct address info pointer, but here it's returning you a linked list of all the addresses. So this is a linked list of addresses. And because this had to allocate that linked list, it does it dynamically, I believe. It's important that you invoke free address info with the result list when you're done. And I didn't leave myself enough room above, so I'll just write it below. That is going to be of type struct adder info pointer. So this one up here does a DNS lookup, returns 0 on success, or it returns a number of error codes if there's a problem, one of a number of error codes if there's a problem. Free address info will free the memory allocated by get address info. So in this course, you're expected to, wherever you have a call to get address info, to have a matching call to free address info. And same with malloc, you're always expected to free whatever you malloc. Otherwise, we'll consider that you've got a memory leak, whether it's in your lab code or really it's the lab code where that matters, but good form for the test too. Okay.